Hi, my name is Brian Durham. Today we're going to be discussing analyzing solar PV farm suitability for properties in North and South Carolina. My background is in GIS. What I did was essentially map out every piece of land in North and South Carolina that is suitable for solar PV development. I'm putting this into a really easy to use platform, so hopefully people can make smarter, faster, more informed decisions so they're not wasting time during the due diligence process looking at sites that just aren't going to work out for solar PV. I've developed a flexible model where we can easily tweak the inputs to change the results if someone has very specific criteria that they're looking for their PV farm. The hope is to eventually, in the very near future, expand this data set to cover not just North and South Carolina, but the entire United States. So why should we worry about going solar? Well, climate change for one, and all of us in this program are well aware of what the problems are. We are emitting greenhouse gases at a rate that is unsustainable, to say the least. So by adding new clean energy to the grid, especially solar PV, we can reduce our emissions faster to hopefully prevent the worst potential impacts of climate change. Greenhouse gases, of course, there's a very clear link between greenhouse gas emissions, CO2 in the atmosphere, with our climate. So the more CO2 that's in the atmosphere, the higher the global temperature is going to get, and the higher sea levels will rise. This isn't anything new. This is a very well-known historical trend that we've seen in the past. But as you can see from the chart, our CO2 levels are truly unprecedented anywhere within the last 400,000 years. Why are we looking at North and South Carolina? Well, the Southeast has recently emerged as a leader in new solar PV installations. Back in 2015, 22% of the projects installed were in the Southeast. In 2016, that went up to that was at 21%. But then in 2017, it was actually up to 40%. So there's a lot of land that's suitable in North and South Carolina. At least that's the hypothesis that I went into this with, and I wanted to help map those out. And actually, 16% of all projects installed in 2017 were actually in North Carolina. So for the electricity sector, also 25% of global emissions are for producing electricity and heat. So if we can eliminate the energy that is used from fossil fuels for producing our electricity, that's 25% of our emissions that we can stave off. For this analysis, I did this with a multi-criteria decision-making technique and specializing in analytical hierarchy process. And basically what that is a fancy way of saying we're going to take multiple data sets and we are going to rank specific pieces of those data sets differently. And that's just based on their importance. So how important are each of these different pieces of data to determining the best spots to put solar farms. And all this is going to be done in GIS, Geographic Information Systems. So we'll be able to take all this data and then map it all out. So basically, all of these different data sets are going to be stacked on top of each other, and then the values are going to be added up. So here you can see, for example, the National Land Cover data set. Land cover's going to be weighted at 19%. Distance to transmission lines will be weighted at 15%. So these are more important data sets than, say, something like our soils, which is not that essential, but having good soils are better than having bad soils. So we still include them in the analysis, but it's not a make or break data set. All of these different data sets were collected and then we have to process them so that they're going to work in our model. And this is an example of one of the geoprocessing models that I built for this analysis. So we go out and we acquire data sets from a variety of sources. Most of them are federal, and most can be acquired at no cost. We did have to acquire the transmission lines and substation locations, but everything else can be freely acquired online. So using the values that I showed on the previous table, these data sets are converted from polygons to raster, and each data type is assigned a specific value. So this model that I built is going to prep the rasters for the cost-weighted overlay. And essentially what the cost-weighted overlay is, where we take all these different data sets and we add up the values to make one data set. So let's take a look at what I actually mean by this. So here's an example of our wetlands data set, the National Wetland Inventory, where on the left slide, all of these are all polygons, so drawn on the map. So it's a vector style data set. And I convert these shapes that have different data types, which you can see in the legend there, where something is considered a lake or riverine or freshwater pond. All I'm going to do is take each of those different data types, and I'm going to convert all of those to a numeric value. So if it's a wetland, in this example, I score that as a 1. So that means bad. We don't want to develop in wetlands. And if it's in the high ground, which is everything shown in white on the left side, then that is going to receive a value of 100 for good. So after all of the data sets are rescored in a similar way, we perform the cost-weighted overlay. And that basically combines all those different data sets. All the data sets get stacked on top of each other, and then their values are added up. And then those added up values are what comes out of the cost-weighted overlay. And we reclassify everything so that it's on a nice scale from 1 to 100, where 1 is low, meaning not suitable, and 100 is good. There's certain areas that we do not want to include in our analysis, so we remove those out and automatically rescore them to 1. So if there's a boundary for an airport, even if it seems like it might be perfect for development from some of the other data sets, we know that in reality that's bad, so that's going to get classified as 1. The same is true for state and federal parks. Residential neighborhoods are bad. We don't want to you're not going to put a solar farm right in the middle of a neighborhood. Open water, we're not looking at any kind of floating solar farms or anything like that in this analysis. So if it's something that's not considered suitable, we remove that. And this is what that ends up looking like in the middle. So you get that score from 1 to 100, where you see a lot of these areas in blue. That means that they either have a low score or it's something that we remove. So if it was in a flood hazard zone, open water, things like that, it automatically gets pulled out. But you can see as the color goes from blue to kind of that tan color all the way up to red, that shows that score changing, where 100 is going to be the darkest red color. So we take that 1 to 100 value, and then we're going to classify them. We're going to break it down to 3 different categories to make it simple. So if the value is between 0 to 65, we're just going to say that that's not going to be suitable for development. From 66 to 75 is going to be potentially suitable. From 76 to 85, it's suitable, and for 86 to 100, it is going to be considered very suitable. And this is what the output ends up looking like. So this is the North Carolina and the South Carolina data sets, all combined, all shown on the map here. And what I'm sure you notice, we did score that transmission line as an important criteria, the distance of the transmission lines. So you can really see those transmission lines stand out with the final output. Now, how is someone going to actually use this data set in real life? We can take this data set and we can add it to any GIS application. We're going to look at this in GeoThink, which is the web GIS software that I've helped develop over the last 10 years with our awesome team of GIS analysts and web developers. So we've inserted the layers into GeoThink, and you can simply check them on, and then you can view the data. You can't really tell a lot when you're zoomed out to this scale, but as you zoom in, you see that this starts to show up and make a little bit more sense for what you're actually looking at. We can turn on the aerial photography in the background and zoom in tight. Let's look at this area that seems to be very suitable for development. We can check this on and off. Looks pretty flat, no trees. Let's check out the wetlands real fast, maybe see if it happens to be wet or not. No, it actually looks pretty good. So it's higher elevation, so that checks out. So you can check out a site really quickly and easily like that. But we can also, since we merge this with a property data, we can actually click on the property, and then we can instantly see what the parcel ID number is, what the property is zoned, who owns it, what their address is, so you can contact them. And then down here, we can actually see our suitability fields that we created. So potentially suitable, suitable, and very suitable. So we know how much land we actually have to potentially develop for this site. So we know that we can interact with the data with other layers, but how does this actually stack up against existing solar sites? So let's check out some existing solar farms. This is the Fairmont Solar Farm up in North Carolina. And there you can see the solar panels. And it shows up in the model as being pretty suitable. Let's go to Darlington, South Carolina and check out this one. Again, looks like the model says it's a good spot for it, and the existing solar farm seems to agree with that. We'll go and check out the Waco farm, also in North Carolina. Again, here's suitable, very suitable. Looks pretty good. And one more for the Triplet Solar Farm. And again, looks like everything is matching up fairly well. Now we've seen how we can zoom out in and out of properties. We've seen how we can look at them on a map. But if I'm a developer and I'm actually searching for land, what can I do? So we're going to select our layer that we've merged for our property ownership with the solar suitability model. I'm going to say that we're looking for suitable acreage that is greater than or equal to, we'll say 50 acres in this example. I'm going to click Run Search, and just like that, we see all these properties highlight on the map. So I'm going to create a quick graphic so we can actually see all these. So there you go, you see them pop out on the map in blue, and I can scroll through the table of our results of each of these properties, and we see them highlight on the map as I scroll through. Then we can click on a property to actually take a closer look at it. So we can look at the site, see what we think, and I can even chart my results as well. So I can see a breakdown by county, how many properties actually meet our criteria. And I can see in Northampton there's 10, so that is the largest number of properties that meet our criteria. And I can even aggregate this data by the acreage, so I can see which counties have the most suitable acreage for solar PV development. And again, Northampton happens to have the most with 791 suitable acres. So we can get really nerdy with the data. We can dive in and we can start answering questions really quickly. So again, the goal for this is that we hope that this will make people work more efficiently. We hope that it'll make people work faster. They'll spend less time on due diligence. We hope that they'll be able to assess properties very quickly using this data set. So instead of having to zoom into all these different properties individually, look at all the different data sets, look at all the different layers that they have to do, relying on 15 different sources all to find the same information. We hope that by having this data set built will allow people to make fast, intelligent decisions and be able to determine which properties are worth pursuing, which ones are not worth pursuing in just a matter of minutes instead of spending hours on each site. So hopefully by doing that, they'll have more time to work on projects that are going to work out, and that will lead to more clean energy being put on the grid faster than the way developers are currently able to do that. So hopefully this all works out as planned, and we end up doing a little bit of good with this data set. My references for my project are included here on this slide. I just want to thank you so much for taking the time to watch this presentation. If you're interested in any of the processes I use to create this data set, or if you're interested in being able to access the solar PV data set, or if you happen to work in a market that is outside of North and South Carolina and you'd like to see us expand this, please feel free to reach out to me with my contact information on the title slide. Thank you again so much for taking the time today.